NEC section 430.52 addresses the overcurrent protection of motors. The overcurrent device for a single motor must be capable of carrying the motor's starting current and must not exceed a value calculated by multiplying the motor's full load current by a specific factor. These factors are 1.25 for single-phase motors, 1.56 for two-phase motors, and 1.3 for three-phase motors. An exception exists where the motor has a service factor of not less than 1.15. In this case, the motor's full load current may be multiplied by the service factor instead of the previously mentioned factors. The key point of contention often arises when a calculated value does not correspond to a standard ampere rating of a fuse or circuit breaker. NEC 430.52 states that in such cases, the next highest standard rating shall be permitted. The interpretation of shall be permitted is crucial. This phrase indicates that rounding up to the next higher standard size is allowed but not mandatory. Therefore, it is permissible to round either up or down to a standard fuse or circuit breaker size, provided that the overcurrent device does not exceed the calculated value derived from the initial multiplication using the appropriate factor. The primary function of motor overcurrent protection is to safeguard the motor from damage resulting from excessive current. The calculated value for the overcurrent device is determined based on the motor's full load current and a safety factor. Rounding down means the overcurrent device offers less protection to the motor but still adheres to the requirement of not exceeding the calculated value. Conversely, rounding up provides greater protection but results in a slightly oversized overcurrent device. While rounding up is generally advisable for enhanced safety, the NEC does not mandate it. Let's delve deeper into the implications of each approach. When rounding down, it is essential to ensure that the selected overcurrent device can still adequately handle the motor's starting current. Motors draw significantly higher current during startup than during normal operation. If the overcurrent device is too small, it may trip unnecessarily during startup, leading to nuisance tripping. The motor starting current is also known as an rush current or locked rotor current and can be several times higher than the full load current. Dual element fuses, also known as time delay fuses, are often used for motor protection because they can withstand the high starting currents without tripping, while still providing overcurrent protection. Another consideration is the motor's operating environment. If the motor is subjected to frequent starts and stops or operates in a high ambient temperature, it may be more susceptible to overheating. In such cases, rounding up to the next standard size may be beneficial to provide additional protection. However, it is crucial to avoid oversizing the overcurrent device excessively, as this can reduce its effectiveness in protecting the motor from smaller overcurrents. It is a balancing act between providing adequate protection without causing nuisance tripping. Now, let's discuss the standard ampere ratings of fuses and circuit breakers. These ratings are defined in NEC Article 240. The standard ratings include 15, 20, 25, 30, 35, 40, 45, 50, 60, 70, 80, 90, 100, 110, 125, 150, 175, 200, 225, 250, 300, 350, 400, 450, 500, 600, 700, 800, 1000, 1200, 1600, 2000, 2500, 3000, 4000, 5000, and 6000 amps. When selecting an overcurrent device, it is important to choose a standard rating that is close to the calculated value but does not exceed it unless rounding up is deemed necessary and acceptable within the code. It's worth noting that the NEC also addresses motor overload protection in section 430.32. Overload protection is intended to protect the motor from running overloads, which are smaller overcurrents that can occur due to mechanical issues or excessive load on the motor. Overload protection is typically provided by thermal overload relays or electronic motor protection relays. These devices are designed to trip at a lower current level than the overcurrent device and provide more sensitive protection against overheating. Both overcurrent protection and overload protection are essential for ensuring the safe and reliable operation of motors. Overcurrent protection protects against short circuits and ground faults, while overload protection protects against running overloads. In summary, when sizing overcurrent protection for a single motor, the calculated value should not be exceeded. If the calculated value does not correspond to a standard fuse or circuit breaker size, rounding up to the next higher standard rating is permitted, but not required. Rounding down is also permissible, as long as the overcurrent device can still handle the motor's starting current and provides adequate protection against overcurrents. The decision to round up or down should be based on a careful assessment of the motor's application, operating environment, and the need for both overcurrent and overload protection. Always consult the NEC and other relevant standards for specific requirements and guidance. Consider these points when making your determination. Firstly, the motor's nameplate full load amps. Secondly, the applicable multiplication factor from NEC 430.52, considering the motor type single-phase, three-phase, etc., and service factor if applicable. Thirdly, calculate the maximum allowed overcurrent device size by multiplying the full load amps by the factor. Fourthly, determine if the calculated value matches a standard fuse or circuit breaker size. Fifthly, if the calculated value is not a standard size, decide whether to round up to the next higher standard size or round down, keeping in mind the considerations discussed earlier. Sixthly, verify that the selected overcurrent device can handle the motor's starting current without nuisance tripping. Seventhly, coordinate the overcurrent protection with the motor's overload protection to ensure comprehensive protection. Eighthly, document the calculations and rationale for the selected overcurrent device size. Ninthly, ensure that the installation complies with all applicable NEC requirements and local codes. Tenthly, if in doubt, consult with a qualified electrical engineer or inspector. Remember that the NEC is a complex and evolving document, and it is essential to stay up to date with the latest revisions and interpretations. Also, local codes may have additional requirements or restrictions that must be followed. Therefore, it is always best to consult with a qualified professional to ensure that the electrical installation is safe and compliant. Let's consider an example to illustrate the application of these principles. Suppose we have a 100 horsepower, 460 volts, three-phase motor with a full load current of 124 amps. According to NEC 430.52, a maximum allowed overcurrent device size is calculated by multiplying the full load current by 1.3. This gives us 124 amps times 1.3 equals 161.2 amps. Since 161.2 amps is not a standard fuse or circuit breaker size, we have the option of rounding up or down. If we round up to the next higher standard size, we would select a 175 amp fuse or circuit breaker. If we round down, we would select a 150 amp fuse or circuit breaker. In this case, let's assume that the motor is used in a critical application where downtime is costly and the motor is subjected to frequent starts and stops. In this scenario, it may be prudent to round up to the 175 amp overcurrent device to provide additional protection against nuisance tripping. However, it is essential to verify that the 175 amp overcurrent device does not exceed the maximum allowed value based on the motor's nameplate and other relevant factors. It is also crucial to ensure that the motor's overload protection is properly sized to protect against running overloads. Ultimately, the decision to round up or down should be based on a careful engineering judgment taking into account all relevant factors. Remember, it is always better to err on the side of safety and provide adequate protection for the motor. By following these guidelines and consulting with qualified professionals, you can ensure that your motor installations are safe, reliable, and compliant with the NEC. The NEC is not intended as a design specification or an instruction manual for untrained persons. It is intended to safeguard people and property from hazards arising from the use of electricity. Therefore, it is essential to have a thorough understanding of electrical principles and practices before attempting to apply the NEC requirements. The proper application of the NEC requires knowledge, skill, and experience. It is not a substitute for sound engineering judgment. Always consult with qualified professionals when dealing with electrical installations. Motors can be designed for different purposes, such as constant speed, variable speed, high torque, low torque, and so forth. These different characteristics need to be taken into account when selecting motor protection. Motor efficiency is another critical factor to consider for energy savings, especially for large installations. High-efficiency motors will reduce your energy costs and carbon footprint, and proper overload and overcurrent protection will ensure that the motor operates safely and reliably, maximizing its lifespan and return on investment.